Let's study small movements of an elastic string. Let's assume that a string is stretched between points x equals 0 and x equals L. We assume that it's stretched horizontally and there are no external forces acting on the string. We are going to study only a small vertical of that string, so we assume that there are no horizontal movements. And if there are, we just consider them too small and disregard. Moreover, we assume that there is no damping in this model. Denote by U the vertical displacement at point x at time t. We denote the tension along the string by the capital T. It's the same at all points of the string. Now let's consider a small segment of the string between the points x and x plus delta x. What forces act on this segment? There is a force coming from the tension on one side and the force coming from the tension on the other side. We are going to write the second Newton law for the vertical movement of the string of this segment that we discuss here. First, let's denote the vertical component of the tension by V. For our segment, there are two vertical forces at the left side and at the right side. Okay, now we are ready to write the Newton second law. So the total force acting on our segment of the string is going to be V of x plus delta x t minus V of xt. So that's the total vertical force acting on this segment. And it must be equal to the mass of the segment. Now, what is the mass of the segment? So we assume that the string has density rho. It's a linear density. It's measured like in grams per centimeter or something like that. So we would have the density rho multiplied by the length of the string. That will give us the mass, and multiplied by the acceleration, vertical acceleration. So it will be the second derivative with respect to time of the vertical displacement. Now, that acceleration will be at the center of mass, which we denoted by x bar. Now let's divide both sides by delta x. So the delta x on the right side cancels. And now we take the limit as delta x goes to 0. So at the left side, we will have the derivative of v and at the right side, we'll have rho multiplied by the second derivative of u at xt. We saw that the vertical component of the tension equal to the linear density of the string multiplied by the second derivative of the vertical displacement of the string. This equation is takes place at every point x. Now we want to get rid of v in this equation by expressing it in terms of u. Since we only study small displacements of the string, at every point the slope of the string is small. So cosine of the angle that the string forms with the horizon is almost 1. So that means that the horizontal component of the tension is equal to almost the tension itself. Okay, so that's what we will be using next. Now, the vertical component of the tension, which is T times sine theta, we can express in terms of the horizontal component. So it will be the horizontal component times the tangent theta. Now, so the horizontal component, as we just mentioned, is approximately the tension itself. As to tangent theta, that's just the slope of the string. So it is equal to the derivative of the vertical displacement of the string with respect to x. Okay, so our equation becomes, so we replace v with t multiplied by partial derivative of u with respect to x. So we get t times that partial derivative. Now, in our equation, we had derivative of v with respect to x. So we need to differentiate tux with x again. And this is still equal to rho times the second derivative of u with respect to time. Now, the tension is constant along the string, so we can pull it out of the derivative. So we have t u, second derivative of u with respect to x equal to rho u second derivative of u with respect to t. Now, traditionally, this in this equation, the second derivative with respect to time is isolated, and the equation becomes a square the second derivative of u with respect to x equal to the second derivative of u with respect to t, where a square, that's the term which is traditionally used, that's notation which is usually used. That's simply the tension of the string divided by the linear density. Okay, so the standard equation, one-dimensional equation of the string, of the small oscillations of the string, is a square times the second spatial derivative of u equal to the second temporal derivative of u.